Okay. So today in this session, we will be discussing about the problems that we covered during the lectures regarding microstrip patch antennas. So I have given you 3 assignments asking you like to solve a problem related to microstrip patch antennas. So I will share the screen. I think in the assignment number uh, assignment number 5 and onwards, I have given some questions asking you to answer the problems using the theory knowledge that we have gained during the lectures. So this is one of the questions. So in this question, we are talking about the microstrip patch antenna and the electric field distribution in the patch. So in order for us to mathematically model the electric field distribution, we are using cavity model, and we have learned that we are considering a specific scenario uh, under the assumptions of the cavity model, and based on that we are considering that the electric field distribution is following a certain like a cosine function, and then we uh, drew the electric field distribution in the patch antenna. Once we have a certain signal uh, fed to the antenna across a certain side of the antenna. So we also learned how the electric field distribution is like getting generated based on the feeding position uh, of the wave. So we are feeding a certain wave to the antenna. So based on the dimensions of the antenna and like in what position we are feeding the wave to the antenna, the electric field which is generated in the patch is varying. So in this question, we are basically asking about that concept. And so during the class, I think we discussed about this a problem. So the first question is like state the assumptions made in the cavity model of analyzing microstrip antennas. So in the lecture notes, uh, I have given the assumptions of the cavity model. So I think you can directly, refer that and write the answers for that. Secondly, I have asked this question where you are asked to consider a rectangular microstrip antenna of dimensions 3 centimeters into 2 centimeters. Its substrate has a relative permittivity of 3.2, and its lowest resonant frequencies of the antenna when it's fed with a microstrip feed line at the center line positions needs to be found. So you need to first consider like what is the mode in which the patch antenna is working. So we are considering a patch antenna of length 3 centimeters and 2 centimeters, right? So I think in the question, okay, I need to give the like A and B positions, right? So if we consider that the patch antenna has a length of 2 centimeters in this side and 3 centimeters in this side. So in that case, once the feeding line is connected to the point A, then the value which is facing the feed line is going to be 2 centimeters, right? So 2 centimeters is lower than 3 centimeters. So because of that, based on the theory we have learned, if the L value, so we take the value which is in front of the feed line as the L value, and we take the other dimension as the W. So this is the standard convention we are following in this type of scenarios in order to find out the mode of the operation, right? So we are taking that the dimension which is facing the feed line is L, and we are taking the dimension which is remaining as W. Okay, I hope you can understand. So in this case, since L is smaller than W, the mode of operation is 0, 1, right? So based on the mode of operation of 0, 1, we can find the lowest resonance frequency using the equation that we have given in the lecture notes. So we have like a square root, and then we have two expressions related to M and N. So you need to substitute values for M and N. So M is going to be 0 and N is going to be 1. So the frequency value you can find using the function which is defined by the Mn values. So you need to substitute 0 for M and 1 for N. So using that, you can find the lowest frequency. So this one you can define for the case where we feed at position A. So the lowest frequency F when we feed at A is going to be the value that you calculate from the equation once you substitute 0 and 1. And when we consider the next scenario where you have the wave getting fed at the position B, the L value is going to be the length of the side which is facing the feed line, which is 3 centimeters, and W is going to be the other dimension. So we need to again we need to consider the length L, the L dimension as the side which is facing the feed line, and the other side as the side with the length W. Right? So in the case where we feed the signal at point B, we have the condition that the L value is higher than W. So in that case, our mode is going to be 1, 0. And based on that, we need to calculate the frequency, right? So our mode is going to be 1, 0 because our length is, or not length, actually L value is higher than W, right? So I consider this as L value because our L value changes based on the feeding position of the wave. So in here, like the mode is going to be 1, 0. Based on the mode, we can calculate the frequency using the equation that we have covered in our lecture notes. So it's basically based on Mn values. So Mn values are like M is equal to 1 and N is equal to 0. So based on that, we can find the frequency, lowest frequency. for the case where we feed the wave at point B. So likewise, we find the lowest frequencies for both the scenarios. And in the next part of the question, we are asking the question that what is the electric field distribution once you feed the wave in the A position. So, so we have a coordinate system that we need, that we consider in this scenario. So if we take the coordinate system as like the axis which is going across the B position as Y, and the axis going across the A position as Z, then we can define the electric field distribution along a certain plane. So this is Z, let's say. So once you feed a certain wave at the position B, the electric field is this distribution is formed across the XY plane, right? And then once you feed the wave at position A, the electric field distribution is formed across the XZ plane, right? So, so the answer to the third question will be like at position at feeding position at A, the electric field distribution is going to be across XZ plane, right? The E plane is going to be across the XZ plane, and at feed position, B, we have the E plane across the XY plane, right? So, so basically the E field is changing across the plane that you are feeding it into, right? So X is in this direction, Y is in this direction. So once you are feeding in the like at B position, so suppose this is the B position, then the electric field is going to change across the XY plane in this manner, right? So similarly, once you feed the wave at position A, the axis of uh, axis of the the Z axis is going to be the other axis which will form the E field. So the E field will be across the X and Z axis. Okay, so E field is going to be distributed like this, and it will be across the XZ axis. So the E field is generated in the XZ plane. So in this case, the wave will be generated in the Y direction. The magnetic field will be generated in the Z direction. Electric field is in the X direction. So therefore, the electric field will be generated across the XZ plane. So I think I hope it is clear to you how the E plane is defined for each feed positions. So now let's consider the next question that we considered in our lectures. So this one. So the next question we have actually considered this is the question that we have considered, and this is with regard to the uh, insert feed technique, and how to find the insert feed length. Once you uh, know the values of the certain parameters like relative permittivity and the characteristic impedance of the feed lines, we can find the value of the insert feed length, uh, which is required for us to like design the antenna such that the feed line is matched to the antenna. So once you directly connect the feed line to an antenna without this insert feed method, there's some mismatch between the impedances of the antenna and the feed line. So in order for us to reduce that mismatch, we are trying to find the position where the characteristic impedance of the feed line is equal to the impedance of the antenna. So the impedance of the antenna is varying across the like plane of the patch in the as given in this function, where you have a cosine function. So based on this function, we can identify how the impedance is changing across the antenna. So uh, since we want to match the like antenna impedance with the feed line impedance, we need to substitute the antenna impedances and feed line impedances into this equation, and then we need to find the insert feed length. So first what we need to do is find the uh, impedance of the antenna, right? So in order for us to find that, we need to find the value of the GIN. GIN is the 1/over value of the impedance of the antenna, right? So GIN value is defined using the W and the lambda parameters. So W in here means the width of the patch antenna, and the lambda is the wavelength of the wave which is propagating along the antenna. So since we have been given the frequency with which no, we need to find the frequency also. Okay, so once we find the frequency, we can find the lambda value of the wave propagation, and then using that lambda value, we can find the value of the GIN, because the width of the antenna we already know. So the W value you can take as the 2.5 centimeters, because in this question, we are considering like a case where we have a square shaped antenna. So the sides are equal. So length and width are equal. So we can take W as 2.5 centimeters. And then for the lambda value, you need to first find the lowest resonant frequency. So since this patch antenna is working like this is a square shaped patch antenna, the lowest frequency that is obtained under both like 10 and 01 modes are equal. So because of that, you can use either 01 or 10 mode, and you can find the relevant lowest frequency based on that, right? So once we can find, actually now the resonant frequency you can find using the equations that that define the that is defined by taking the value of the like by I mean, for each mode that we are considering, we can find the resonant frequency, right? So in the lectures we have learned the equation for the resonant frequency, and it is depending on the m and n values, right? So it is a function of m and n. So if the mode is 0 1, the m value is 0, n value is 1. So by substituting these m and n values for m and n into the function, you can directly find the value of the frequency, right? So I think it's going to be something like v over 2l or something, right? So the v here is going to be the wave speed in the certain material that we are considering. So the v is not the speed of light, but speed of light divided by the square root of the relative permittivity of the material. So the relative permittivity value has been given in here as I think 2.6. Therefore, you need to substitute that value and then find the velocity of the wave in that medium. And then you divide by the length of the divide by the 2 into length of the antenna, right? So length of the antenna is like 2.5 centimeters. So you can convert it into meters also. So it's going to be uh, 2.5 into 10 to the minus 1. And then using that, you can find the frequency of the wave. And then once you find the frequency of the wave, you can find the wavelength of the wave. So using the relationship that C is equal to F lambda, you can find lambda is equal to C over F. Right? So C is 3 into 10 to the 8, and F is like uh, the value that you found here, which is F naught. Using that, you can find the lambda value, and then you can maybe convert it into meters, right? So once you have converted like that, you can find the value of GIN, which is 1 over 45 into W over lambda squared, right? So W value you know as say 25.5 centimeters, which you can write 2.5 into 10 to the minus 1. And then lambda value you can find as a lambda naught value using this equation. So you can substitute the lambda naught value and then you can take the square of it. Then you will find a certain impedance value, but it will be 1 over uh, impedance of the antenna, right? So you will get 1 over R in. So from the from this equation, you need to find the R in by taking 1 over GIN value. And then once you find the R in value, you can find the inside feed length that is required to like match the feed line to the antenna. Right? So the R in value, which is occurring at y equals 0, must be made equal to the impedance of the feed line, which is I think 200 ohms. And using the cosine function, I mean, I'm basically substituting the values of the impedances of the antenna and the feed line into the equation that has already been given in the question. So this is the equation that has been given to us. So what we need to do is just substitute the impedance values of the antenna in this position and substitute the value of the impedance of the feed line in this position, right? So the antenna impedance, we can get some value like maybe 467 ohms or something, right? So based on that value, you can find a value for the cos squared function here, right? So you will then have to take the square root of this value to find the cos phi y naught over L value, right? And then you need to take the cos inverse of that function. Then you will find some, right? So some value for this uh, side, right? So I think you can solve this equation and finally find the value of y naught, right? So y naught is the inside feed length. So in here, this is the phi value, which is 3.14. Then L value you already know. So you can find y naught using this equation, right? So that is all that has to be done with regard to that question. Right after that, we have the next question, which is about the balance matching. Right. So in this question, we have to consider a dipole antenna, which has an input impedance of 85 plus 50J. And we have been given the frequency with which this dipole antenna is working, which is 1.5 gigahertz. It is fed by a 50 ohm coaxial transmission line, and then a lambda over 4 coaxial balance is connected to the system. So first we are asked to draw a diagram of how the dipole is connected to the balance. So basically we have learned about the balance matching in the lectures. So in there we learned that like we connect a balance across the like one arm of the antenna and the outer surface of the coaxial cable, which is connected to the other arm of the antenna, right? So this is the coaxial cable, right? And the other arm is connected to the inner conductor of the coaxial cable, and the conducting wire is connected to the one arm of the dipole antenna and the coaxial cable's outer surface. So the conducting wire is of length lambda over 4. So basically we are specifically selecting a conducting cable of lambda over 4 in this scenario in order to obtain a specific impedance at the outer surface of the coaxial cable. So according to like transmission line theory, the a conducting wire with length lambda over 4 has a impedance of uh, has an impedance JXP, which reaches infinity when the length is lambda over 4, right? So the conducting wire has zero resistance. It only has an imaginary resistance impedance, right? So this value reaches infinity uh, once the length is lambda over 4. So once we connect a balance like this to the dipole antenna, there's no effect from this connected balance or this conducting wire to the antenna system, because the impedance of this balance is like or reaching infinity, and once it is connected in parallel with the antenna feed point, then because of the parallel connection, the resulting impedance at the feed point is equal to the antenna impedance. So there's no effect from the impedance from the balance. So we can show that using mathematical derivations also. So the now what we are trying to find out here is whether there's effect from the balance to the impedance of the antenna system once the balance is connected to the system. So once the balance is connected, the final resultant impedance is going to be equal to input impedance of the antenna in parallel with the impedance of the conducting wire, right? So the conducting wire I'm representing here as like Z naught, for example. So Z naught is going to be like JXP, um, which is reaching infinity, right? So uh, once these are parallelly connected, we can write the expressions as Z in into JXP divided by Z in plus JXP, right? Z in plus JXP, right? So in order for us to make the calculations easier, we are considering admittances on both sides. And then we can divide the like impedances easily since we have the product of the impedances in the denominator. So once we like divide each of these terms by the denominator, we can get the like expression 1 over jxp plus 1 over zn, right? So this is going to be 1 over zn, z sum. And then since the jxp is reaching infinity, the 1 over z sum is going to be equal to 1 over z in, which means that z sum is equal to z in, which means that there's no impedance effect from the jxp or the impedance of the balance. So this is a really convenient scenario for us because the balance that we connect to the system in order to reduce the like leakage current is like uh, prevented using the balance while also not adding any impedance, additional impedance to the system. Okay, so next we will check the next part of the question. So in the second part of the question, we address the fact why we are adding like a balance of lambda over 4. So for the first reason is that we are trying to reduce the leakage current over the coaxial cable by using a conducting wire of lambda over 4, which has a high impedance due to its length. So because of its high impedance, the leakage current across the coaxial cable is going to be minimum. The second reason is that the balance does not add additional impedance to the antenna uh, because the parallel connection of the conducting wire with the antenna results uh, in a in the situation that the final impedance is equal to the impedance of the antenna because the impedance of the like balance is reaching infinity. So I think the second question answer is clear, and if you have any questions, you can uh, write to me and also meet me and get it clarified. And now let's talk about the next question, which is if a capacitor is connected in parallel at the feed point in order to make the antenna self-resonant and match to the feed cable, calculate the required capacity, right? So the third question is like connecting a capacitor in parallel to the feed point of the antenna. So first we need to visualize the situation. So we need to draw a diagram uh, and like showcase how this connection is done, right? So we have the dipole antenna connected to the coaxial cable. We have a balun which is connected to the system. So our balun is like uh, having a conducting wire of lambda over 4. So in here at the feed point of the antenna, we have a capacitor connected in parallel. So this capacitor will have a impedance of 1 over j omega c, and then the sum impedance that is occurring at the feed point will be the input impedance of the antenna in parallel with the input impedance of the capacitor, right? So a capacitor impedance I will represent using ZC. So just like before, we can write the total sum impedance as the product of the impedances and divide by the sum of the impedances. And then since we want to make the calculations easier, we are considering admittances on both sides. And then we can write that 1 over Z sum is equal to 1 over Z in plus 1 over ZC. So Z in value, we are given in the equation, in the question as 85 plus 50J, I think. So you need to substitute that value in here. So you can find the value of this 1 over 85 plus 50J using maybe MATLAB, right? So you don't need to manually calculate those things. So 1 over ZC. So 1 over j omega c means j omega c, right? So omega c value you need to calculate, right? So c value you are trying to calculate. Omega value you know based on the equation omega is equal to 2 pi s, right? So omega you can find 2 into 3.14 into the frequency, which is 1.5 into 10 to the 9. So using this, you can find some value for omega, which I will represent as omega naught. So as the final expression, you will get something like for this first expression, you will get a resulting impedance value, which is in the form A minus BJ, for example. And then you can find J into some omega naught into C, right? So in order for us to match the coaxial cable to the antenna, the final impedance at the feed point must be fully resistive. If there's some imaginary component to that impedance, that means the feed line is not connected to the dipole in a fully matched manner. So in order for us to erase the or cancel out the imaginary component or imaginary part of the impedance, only we are connecting the capacitors. So what we want to do with in here is that we need to make the imaginary part of the total resistance equal to 0. So which means that omega naught C minus B must be equal to 0. So since we know the value of B and the value of omega naught, we can find the value of C. So B over omega naught gives the value of the capacitor. So once we connect this capacitor, the imaginary value of the impedance at the feed point is getting cancelled. So that is the advantage of connecting a capacitor in parallel to the feed point of the antenna. So that's all I wanted to present in this session in today's tutorial. So I hope you got an understanding about how to solve this kind of problems and basically these three questions that I discussed today. If you have any questions, you can come and meet me or else write an email to me, or else you can ask questions in the WhatsApp as well. So that's all for today. So I hope you understood. So let's end the session now and we'll end the session.